Simplified pneumatic liquid flow generator. In the previous video, we introduced the pneumatic liquid flow generator capable of generating electricity with very small temperature differences. Since its mechanism is relatively complex, a simplified single-chamber pneumatic liquid flow generator can be considered for those aiming for a similar effect at lower cost. The following explains the principle and provides a rough calculation of the temperature difference required to start the system. As shown in the left image, a bottle is placed on each side of a balance-like structure. A water pipe connects the bottoms of the two bottles, as represented by the purple line in the diagram. One bottle's top has an air pipe open to the atmosphere, shown as the green line on the left side of the diagram. This bottle is defined as bottle A. The top of the other bottle is connected to a sealed air chamber via an air pipe, as shown by the yellow arrow in the diagram. This bottle is defined as bottle B. The air pipe leading to the air chamber is represented by the green arrow in the diagram. The bottle openings outside the water pipe and air pipe are sealed. The air chamber has two water tanks on either side, one for hot water or other heat sources, and the other for cold water or cooling sources. Inside the air chamber, there is a thermal insulation plate, shown as the yellow partition at the bottom of the diagram. Above the air chamber, there is a device to guide the movement of the thermal insulation plate, which is linked to the angle of the balance. To maintain better airtightness in the air chamber, this device can use magnet-to-magnet remote linkage. In the initial setup, low-temperature gas is first injected into the air chamber, and an appropriate amount of liquid is added to both bottles. As shown in the left image, due to gravity, the balance and the thermal insulation plate will tilt to one side. If cold gas is used initially, adjust the balance so that the thermal insulation plate tilts towards the side where cold water will be added. At the same time, bottle B will have more water than bottle A. If hot gas is used initially, the thermal insulation plate should tilt towards the side where hot water will be added, and bottle A will have more water than bottle B. Adjust the air chamber pressure to an appropriate level. Then, pour cold water and hot water into the respective water tanks. This completes the initial setup stage. This time, since the heat insulating plate is on the cold water side, the gas on the hot water side is heated, initiating the gas heating process in the chamber. As the gas temperature rises, the bottle connected to the gas chamber, bottle B, increases its internal pressure, pushing water toward the bottle exposed to the atmosphere, bottle A. Thus, the water level in the B bottle starts to drop, while the water level in the A bottle begins to rise. When the temperature in the gas chamber is high enough to make the liquid in the A bottle exceed that in the B bottle, gravity causes the system to oscillate, initiating the first oscillation process. During the descent of the A bottle, the lower position allows more liquid to flow into it, increasing the oscillating torque, which can be used for power generation. In the first oscillation process, the balance movement shifts the heat insulating plate from the cold side to the hot side, causing the gas to contact the cold side and be isolated from the hot side, thus entering the gas cooling process in the chamber. At this point, the gas is cooled as it contacts the cold side. As the gas temperature decreases, the bottle connected to the gas chamber, bottle B, reduces its internal pressure, drawing water from the bottle exposed to the atmosphere, bottle A, back into itself. Thus, the water level in the B bottle starts to rise, while the water level in the A bottle begins to drop. When the temperature in the gas chamber is low enough to make the liquid in the B bottle exceed that in the A bottle, gravity causes the system to oscillate again, initiating the second oscillation process. During the descent of the B bottle, the lower position allows more liquid to flow into it, increasing the oscillating torque, which can also be used for power generation. At this point, the system returns to its initial state and begins another cycle of heating, cooling, and oscillation. Thus, it can be seen that as long as the temperature of the hot water tank is high enough, and the cold water tank's temperature is low enough, this device can continuously oscillate automatically, and the energy from this oscillation can be used for power generation. Now, let us calculate how much of a temperature difference is required to generate electricity continuously. Assume that a commonly used 2000 cubic centimeter PET bottle is used, with the lowest water level set at 45 millimeters and the highest water level at 205 millimeters during the entire cycle. It is measured that the liquid volume at the lowest water level is 315 cubic centimeters, and the liquid volume at the highest water level is 1,480 cubic centimeters more than at the lowest water level. At the highest water level, there is 365 cubic centimeters of space above the liquid. Assume further that the height difference of the balance pendulum is 200 millimeters. Let the volume of the gas chamber be V.box. At the initial state, the total volume of gas used for pressure regulation is V.box plus 0.000365 cubic meters, as shown in equation 1. When bottle B initially rises to its highest position, the total volume of gas used for pressure regulation is V.box plus 0.001845 cubic meters, as shown in equation 2. When the water volume in bottle A equals that in bottle B, that is, at the turning point, the total volume of gas used for pressure regulation is V.box plus 0.001105 cubic meters, as shown in equation 3. Assume atmospheric pressure is 101,325 pascals. At the initial state, the internal pressure of bottle B is approximately 1.00387 atmospheres, as shown in equation 4. When bottle B initially rises to its highest position, the internal pressure is approximately 0.99613 atmospheres, as shown in equation 5. At the turning point when bottle B begins to rise from its lowest position, the internal pressure is approximately 1.01934 atmospheres, as shown in equation 6. At the turning point when bottle B begins to descend from its highest position, the internal pressure is approximately 0.98066 atmospheres, as shown in equation 7. Assume the average temperature between the high and low temperatures is 25 degrees Celsius, 298.15 kelvins. Since the total amount of gas remains unchanged and the volume at the turning points is very close. According to the gas equation, the temperature difference of the gas in the gas chamber between the highest and lowest temperatures is 11.535 degrees Celsius, as shown in equation 8. Due to practical operation conditions being less ideal, it is reasonable to estimate that the required temperature difference under the selected parameters is about 15 degrees Celsius. Next, we need to estimate the approximate required volume of the gas chamber. Assume the turning process is very fast, and heat exchange during the turning process can be neglected. From the previous calculations, the volume at the turning point from low to high is as shown in equation 3, and the pressure is as shown in equation 6. When it just reaches the highest point, the volume is as shown in equation 2, and the pressure is as shown in equation 5. Using the adiabatic process equation, and selecting the adiabatic constant of air as 1.4, the required volume of the gas chamber is approximately 40 liters, as shown in equation 9. From equation 9, it can be seen that the volume of the gas chamber is within an acceptable range. The calculation of energy efficiency will be introduced in subsequent videos.